Okay, just to make sure I had everything where it needed to be. So anyway, I'm going to put this on one screen. So this is problems 1 through 4. And it's asking us to determine whether the function approaches its infinity or negative infinity as x approaches -2 from the left or from the right. So it's just easier to just point this out. So here's the function, and you can see here's the, we're supposed to be doing -2. So here's x equals -2. You see we have vertical asymptotes. That happens when you factor the denominator and you get x plus 2 and x minus 2. So there's 2 vertical asymptotes. So, of course, this is positive infinity going this way, negative infinity going that way. So, coming from the left here, you see we go to positive infinity, and from the right, we go to positive infinity. Number 2, that's just a simple reciprocal function that's offset by 2 units in the x direction. So we have a vertical asymptote when this goes to 0, which is -2. So again, from the left, you go down to negative infinity, and from the right, you go up to positive infinity. Now, a tangent has vertical asymptotes when the cosine goes to 0, because if you remember, the tangent of x is equal to the sine of x divided by the cosine of x. So when this goes to 0, tangent goes to infinity, or negative infinity, depending upon the sign of this thing here, or sign of both of these actually. So the and that happens when, well, here that's pi x over 4, so it happens at these values of x, -2, negative, positive 2. So we see coming from the left-hand side here that we approach positive infinity, and the right-hand side we approach negative infinity. And then finally the secant, which is 1 over the cosine. So it happens, and then we have the secant of pi x over 4, so we've got the same argument. So it's not surprising that we have the same vertical asymptote locations, because here we have 1 over the cosine, here we have sine over cosine. So they both these functions have vertical asymptotes at the same x locations. Anyway, you can see here from the left we go to negative infinity, and from the right we go to positive infinity. Okay, problem number 10. So the function we're looking at is f of x equals 4 divided by x minus 2 quantity cubed. So the question is, find the vertical asymptote. Well, that's all we're doing is find vertical asymptote. So this is pretty easy. The numerator is always positive because it's a number, positive 4. And so the vertical asymptotes occur when this goes to 0. And so we have a vertical asymptote at x equals 2. Because what we're looking at is when does x minus 2 equal 0, so you add 2 to both sides to get x equals 2. So that's where the vertical asymptote is. It would be the same as for 4 over x minus 2, 4 over x minus 2 squared, 4 over x minus... So even though we have 3 times here, it's still just one vertical asymptote. What happens, let me just give you a little extra bonus here. So here's x equals 2. So what would happen is if you plotted the function 4 over, so we're going to do 4 over x minus 2, it's going to look something like this. Now if you have 4 over x minus 2 squared, because the denominator is squared, it's always going to be positive. So you still have this vertical asymptote, but what happens is it'll come in, it'll go like that, up to positive infinity, and then it'll go up to positive infinity again. So the question is maybe what does the next case look like? 4 over x minus 2 cubed. Well, it looks pretty much like the first case, except that it is more abrupt. So it'll come out here. I know you're really close, and it'll go really fast. So you wouldn't be able to tell a huge amount of difference between those two. Now, actually, let's just go ahead and plot it in the graphing program since we have it so readily available. Let's see if I know what I'm talking about. Okay, so we have 4 divided by x minus 2. And we have 4 divided by x minus 2 squared. So we'll do that first comparison. And so you see the blue curve, which is squared, they go up, whereas the red one goes up and down. Now what I'm going to do is I'm going to change that to cubed. And if I can graph it. So there you go. So this is x 4 over x minus 2. This is 4 over x minus 2 cubed. So you see it has one vertical asymptote. They both go the same direction, but one stays closer to 0 for longer and then takes off and gets bigger quicker. So I didn't quite have it right, but close enough. So we're going to problem number 11. Again, we're just looking for the vertical asymptote. So we have x squared minus 2 divided by x squared minus x minus 2. So if you factor the denominator, which yeah, you can. So let's just factor the denominator first. So you have x minus 2, x plus 1. Now, if to have vertical asymptote, if these go to 0, this would have to not go to 0. And it turns out in this particular case that happens. So, and you really, if you factor the numerator, what would you have? You'd have x plus the square root of 2 and x minus the square root of 2, all divided by x minus 2 times x plus 1. So you see there's no overlap. We're not going to be able to cancel anything out here. If we could cancel out, then we might not have vertical asymptote. We just have a hole. But in this case, we do have 2 vertical asymptotes to just say VA. One at x equals 2, one at x equals -1. So that's it. Problem number 12. So our function is g of x, which is 2 plus x divided by x squared times 1 minus x. So just like the previous problem, if you looked at that, there's no common factor in the numerator and the denominator. We have, this will go to 0 when x is equal to 0, and this will go to 0 when x equals 1. So we have 2 vertical asymptotes. One is when x equals positive 1, because when x equals positive 1, you get 1 minus a positive 1, which is 0, and you get 1 where x equals 0. Again, this is squared, but it's still, you only have one vertical asymptote associated with this. So okay, we're continuing on in section 5. So we're doing problem number 13, finding the vertical asymptotes. So we have the function f of x is equal to x squared over x squared minus 4. So again, find the vertical asymptotes. Take the denominator, which is the bottom, and you factor it. So we'll take x minus 4 squared. X squared minus 4 is going to be x minus 2x plus 2. So when either one of these equals 0, then we have 0 in the denominator. And you can see that if we factor the numerator, there really is the values of where the numerator go to 0 are 0. So we won't have any common factors. So these are two two of the vertical asymptotes. If we had, say, x plus 2 in the numerator, then that would cancel out with this, and you'd end up with a hole there, but not a vertical asymptote. So basically, our vertical asymptotes are at x equals 2. Set this equal to 0 and solve for x. You'll get x equals 2. And set this equal to 0, x plus 2 equals 0. And you get x equals 2. We have a x and y intercept at 0. We have a y-intercept because when you set x equal to 0, you get 0 divided by -4, which is 0. And if you set the numerator equal to 0 and solve for x, you get x equals 0. Now it's a little different because you've got x squared, so it actually just touches the x-axis. So I'm going to switch over to the graph improvement. This has nothing to do with the problem, what they asked for, but it's not that it's not important. So let's just look at this equation and then just kind of talk about the things that are happening. So you've got x squared divided by x squared, quantity x squared minus 4. So we graph it. And let me just fix this here. Let's see if that works. Okay. So you have vertical asymptotes here, -2, +2. And notice that it does intersect at x equals 0. Because we had x squared, we get this where it comes up and it just touches x equals 0. It doesn't go through. If I rewrote this, if I changed it to x over x squared minus 4, then it would intersect the x-axis. So you can see we still have vertical asymptotes at ±2, but here, because we just have x instead of x squared in the numerator, it actually intersects and goes through. Again, if I change it to x squared in the numerator, because it's a repeating root, basically, a repeating value. So just like with quadratic equations and what's the word? Cubic equations, you end up just touching it if that's the case. So there you go. Okay, we are on 15. So our function, instead of f of x, we're just calling it g of x to show that you don't have to always be f. And you also, the variable, and actually it should be g of t because I've got the variable is t, which a lot of times is time. So we look at this, and again, we factor the denominator, but anytime you have something squared plus something, there are no real roots. They're just imaginary roots. So because this never goes to 0, then there are no vertical asymptotes. Now the numerator goes to 0 when t equals 1, so there is an x-intercept at t equals 1. So besides the fact this doesn't factor, the other thing too is if no matter what t is relative to its sign, whether it's positive or negative, t squared is always positive. So this always is positive. So let's just think about how this thing might look. So as t goes to infinity, you get t over t squared. Basically, this lower order terms drop out, but t over t squared is always going to go to 0. So we're going to have a horizontal asymptote of 0. It's going to intersect the x-axis, or t-axis in this case, t and g of t. So it intersects the x-axis when t equals 1, because we set this equal to 0 and solve for t. And if you set t equal to 0, which is going to be the y-intercept, you end up with -1 over +1. So it's going to actually intersect the x-axis here, and it has a horizontal asymptote of 0 because that, and when it goes to negative infinity, you've got a negative number over a positive number, because negative infinity squared is positive infinity, or really negative number. It doesn't matter what the number is. If it's negative and you square it, it becomes positive. So this approaches 0 again, just like it did here, but it approaches from the negative side instead of the positive side. So given that fact, I'm expecting that the function looks something like this. It goes, and then it gets near 0, it gets a little bit bigger. It probably gets a max right here at x equals 0. Then it goes through x equals 1, probably, and then probably zooms over like that, and then when it gets big, it goes down. Something like that. Yeah. So let's plot it. Let's see how close we were. See if I did that all right. If not, we'll fix it. So the function was x minus 1. It's actually t, but the graphing program will only take x is the variable. So we have x minus 1 over the quantity x squared plus 1. We graph it. And there we go. And actually the maximum, or the minimum here occurs a little bit below, because I could use calculus to figure that out, but I didn't really know where this thing popped out. So you can see we approach 0 from the negative side. As we go to negative infinity, we have the y-intercept, negative 1, the x-intercept, positive 1. We come up, and then we have to approach the y equals 0 line as we go to positive infinity. Okay, so that's, now we're going to skip a couple, so we go to 20. So a little more complicated. So we have g of x is equal to 1/2 x cubed minus x squared minus 4x divided by 3x squared minus 6x minus 24. So we have a third order equation in the numerator, but we have the lowest order term is an x, so we can actually factor out an x there. And you say, well, don't we have to just worry about the denominator? But again, I'm actually going to factor out 1/2 x. And what that'll do is that'll make that x squared. This will become negative 2x, and this will become negative 8. Why did I do that? Because if I left a half there, it's just harder to factor. So I factored out a half, and so you'd have negative 1 divided by a half is negative 2, negative 4 divided by a half is negative 8. Okay. And then the denominator we can factor out as 3. So you have 3x squared minus 2x minus 8. Hey, we got the same thing here. We got the same expression. You can factor that. So we can factor both the numerator and the denominator. So you would have x minus 4x plus 2 and x minus 4x plus 2. Now how did I do the factoring? Of course the first terms are x's, and then I knew that the two numbers multiplied together here had to equal negative 8, so that would be either negative 8 and positive 1, the other way around, or negative 2 times 4, or negative 4 times negative 2. And because this was negative, I knew the bigger one of the two had to be the negative one. So 4 and 2 equal 8, and I picked this the negative one because this one's negative, because this has to be greater than that to end up being negative. But what you can see is that you have this this common factor, and so those cancel out. And they cancel out, except the function is not defined at x equals 4 or x equals negative 2. But it's not a vertical asymptote. So if you just did the denominator, you'd say, oh, I have a vertical asymptote at 4 and negative 2, but I don't. I have a hole, which is where the function is indeterminate. So the answer would be there are no vertical asymptotes. And we can always go back to the graphing program just to make sure we did it correctly. So let's do that. So let's put it in here. So the equation was 0.5 times the quantity. Actually, let's do this again. 0.5 times x cubed minus x squared minus 4x, the whole thing divided by 3x squared minus 6x minus 24, close parentheses. Let me just take my glasses off. Oh yeah, see, I got a problem here. 3x squared. I think that's right. So we graph it. Should actually turn out to be just a line, a straight line. So there it is, and you can see it's got this little squiggly thing here, x equals 2, and you don't see that x equals 4. It all depends upon the zooming factor here. Even when I zoom back out again, it disappeared. So anyway, so it's just a straight line, and there are holes at x equals 4 and x equals -2, I think was what we said. Okay, we've got another similar problem here for 24, if you just watch number 20. But we have h of x is equal to, take my glasses off here so I can read this thing, x squared minus 4 x cubed plus 2x squared plus x plus 2. So the question is, can you factor the denominator? And let's just, this probably won't be obvious, wouldn't be obvious to you, but again, since I do these, I've done these a few times. Now, think about what happens here. What I'm trying to do is determine if there's a common factor between these two. And if I let x equals 2, then this would go to 0. But if I let x equals 2 here, it's never going to go to 0 because everything's going to be positive. So x equals 2 is not going to be a common factor between the two. But x equals -2 could be, because you cube it here, and so that's going to be negative. This will be positive. This will be negative. This will be positive. So there's a chance that these things will cancel out if you have x equal to -2, which is from this factor. So that's what I'm going to guess. I'm going to guess that x plus 2 is a factor. So we can use long division to see whether it actually is a factor. So we write down the coefficients of the denominator, and I'm going to divide by x plus 2, well, x minus 2, but when you do the long division, you use, or the synthetic division, you're using x equals 2, which is the 0. This is the factor is x minus 2. That's not correct. I'm trying to do this one. X equals -2 here. So I'm going to have a negative sign. So you take the negative of what this is. So I'm thinking that x equals -2, or the factor x plus 2 equals 0 is the common factor that I might be able to cancel out. Another way you could do it is you could plug in -2 and see whether you get 0 here, because you'll get 0 in the numerator. And so we'll do that too. But let's go ahead and do this. Okay, so you take 1, you bring that down, and then you have -2 times 1, which is -2, and you get 0 when you add those two together. -2 times 0 is 0, so 1 plus 1 is 1. -2 times 1 is -2, and then you add them together, you get 0. So the resulting quadratic equation, so somebody go to at this page. So we can say that x cubed plus 2x plus x plus 2 is the same as x plus 2, okay, because this is associated with this factor, and then multiplied by x squared plus 1, x squared plus 0x plus 1. And if you multiply that thing out, let's just confirm it. So use FOIL, you get x times x squared is x cubed, 2 times x squared is 2x squared, x times 1 is x, 2 times 1 is 2, and so lo and behold, that does work out. Okay, so our original expression, h of x, is going to be x minus 2x plus 2 times x plus 2 in the numerator, and then you're going to have, I'm just switching these two so I can have the common factors below and above each other, so you get that. So now we have, those cancel out and become 1. So there is a hole at x equals 2, x equals negative 2, and you can see the denominator never goes to 0, so there's going to be no vertical asymptotes either. So we can say no vertical asymptotes. If you only looked at the denominator and factored that, you'd say, oh, there's a vertical asymptote at x equals negative 2, but that wouldn't be true because it cancels out here with that common factor. And again, you can plot it and see that's true. So why don't we do that? Okay, so the function, going back to the original function. So we've got x squared minus 4 divided by x cubed plus 2x squared plus x plus 2, close parentheses. Okay, that's right, and I graph it. So there you are. Look kind of similar to the one we just did, is it? Maybe it's exactly the same, isn't it? Because once we simplify, we get, well, it looks the same as number 15, and that, so it simplifies down to that. Except there's a factor of 2 here somewhere or another, so instead of negative 1, it goes down to negative 2. But you can see there's no vertical asymptotes. And let's go back to the original one, because I was going to show you something. What I said was, if you thought that x plus 2 was a factor, then you could just plug it in here. So let me just do that. So if I said, what is h of negative 2? I would stick negative 2 in there. So you'd have negative 2 squared minus 4 divided by negative 2 cubed plus 2 times negative 2 squared minus 2 plus 2. So you get negative 2 squared, which is 4. Subtract 4. So we have 0 in the numerator. And then we have negative 2 cubed, which would be negative 8. We have negative 2 squared, which is positive 4, times 2 is positive 8. We have negative 2 plus 2, so you can see it's 0 divided by 0, and therefore we know that x plus 2, or x equals negative 2, is this common factor. So we kind of know that. You still have to go through this to figure out what the resulting denominator is, but at least you know that it would work out. And we found out it worked out anyway because we had the 0 remainder. This is number 33. So now we're going to actually do some limits. So 33 says, what is the limit as x approaches 2 from the positive side? And you see we have vertical asymptote at x equals 2. That's why we're doing the problem. So because this goes to 0, the denominator equals 0 when x equals it's x minus 2. X minus 2, and what did I, oh, okay, that's right. So you plug 2 in, you get 0 here, and you get non-zero there. So it's undefined, it's So the question is really, does it go to positive infinity or negative infinity? So that's always the question. So there's a couple of ways you can plug in some. You could say, 2 plus is approximately equal to 2.1, and plug it in and see what you get. Okay, so let's just do that. That's one way of doing it. 2.1 minus 3 divided by 2.1 minus 2, which is negative 0.9 divided by 0.1, which would be negative 9. So it's negative. The important thing is it's negative. And as if you let 2 plus approximately equal 2.01, then it would be bigger. It just keeps getting bigger as you approach 2, and then it goes to infinity when x equals 2. Okay, so because this is negative, then we'd say the limit is equal to negative infinity. So that's one way of doing it. You don't actually have to plug numbers in there. You just have to look at what happens. So the way I would do it is I would look at this ratio, and I would say, okay, if 2 is going to be if this is going to be slightly bigger than 2, if this is slightly bigger than 2, well, the denominator is positive. A larger number minus a smaller number is positive. Here I have a smaller number minus a larger number, 2-ish, and you could actually just plug the number in there and say, okay, when x equals 2, that's going to be negative 1, so I know it's negative. So you only really have to think about, the sign of this one. You can just kind of approximate it. Okay, so anyway, so I've got negative divided by positive, and the rule of sign says that if you have different signs like this, then if you multiply different signs together, you get negative. You multiply like signs together, you get positive. And the same with division. If we had a negative divided by negative, we'd have positive. If we had a positive divided by positive, we'd have positive. But if one of these is negative and the other one's positive, then it's negative. So I'm just looking at the sign. So since it says negative, I can say the same thing that I just said here. So I don't actually have to plug any numbers in. Because all we're looking for is it negative infinity or positive infinity? So I'd say negative infinity. Same answer I got over there. This is number 34. So again, we're looking for the limit. So we're taking the limit as x approaches 1 from the positive side of 2 plus x over 1 minus x. So again, the easiest way to do it, not the easiest way, but if you forget how to do it, this is the other way. You can always do it this way. So what we could do is say, let x approximately equal, let x equal 1.1, which is slightly larger than 1. And then we just plug it in and see what we get. So we get 2 plus 1.1 divided by 1 minus 1.1. And so you plug in your calculator. 3.1 divided by negative 0.1, which is going to be negative 31. So that's negative, and therefore the answer is negative infinity. Now, if it was any other number besides 1, we just plug it in there. But because when x equals 1, the denominator goes to 0, then you have to do this plus or minus thing. Okay, so that's the one way of doing it. The second way that I hope you will learn to do, find where the button is there. Okay, so again, you do it on that. You basically do it on an order of magnitude thing, or just a sign thing. So what we're doing is x approaches 1 plus. So you look at the numerator, and you've got a positive number. X is positive. 2 is positive. So positive plus positive equals positive. In the denominator, you've got 1 minus a number that's slightly larger than 1. So if you subtract a larger number from a smaller number, then you get negative. If you subtract a smaller number from a large number, then you have positive. So 1 minus a slightly larger number is going to be negative. And therefore the answer is negative, and it's going to be negative infinity, which is the same thing we kind of came up with here. Once you get close to the asymptotes, unless it's a really weird expression, it's it's just going to go in one direction. So if you know which direction it's going, you know that if this is going to be negative, then it can't go back and cross the x-axis and go the other direction. It's always going to keep going in the way it started going. Number 35. So it's a little more complicated, not that much, but let's see. X approaches 3 from the positive side of x squared divided by x squared minus 9. So the question is, do you have vertical asymptotes, especially at x equals 3? And the answer is yes, because if we factor this expression, you get x squared divided by x plus 3 times x minus 3. So we have vertical asymptote at x equals negative 3 and x equals positive 3. So we're asked to do the limit as we're approaching positive 3. So you could let x equal 3.1 if you wanted to, and then just plug it in. So you'd have 3.1 squared divided by 3.1 plus 3, and then 3.1 minus 3. So you just get your calculator out, and we're surprised I haven't used my calculator. I guess I got lucky. I haven't had to use my calculator. Okay, so let's so you get 3.1 squared divided by 6.1 divided by 0.1, and you get 15, approximately 16. It's positive 16, so that's the important thing, positive 16. So we know the answer is positive infinity. Okay, again, just doing it from an order of magnitude standpoint or a sign standpoint, we look at the original equation. And so we say, okay, x squared as x approaches 3. Well, it's positive. So positive squared is positive. So I'll put in positive and we square that. In the denominator we have x squared. I'm not even going to factor it. So you would say I'm going to use a number slightly larger than 3. Well, if 3 squared is 9, then a number slightly larger than 3 squared is going to be greater than 9. So let me just write that down. If 3.1 is greater than 3, for example, then 3.1 squared is greater than 3, or you could 3 squared. Or you could say, if a is greater than b, then a squared is greater than b squared. Is that true? Well, that's true if a is greater than 1, or a and b are greater than 1. So that's not always true. If you had a half and a third, then that wouldn't be exactly true. But if it's a number greater, which it is in this case, it's greater than 1. Both are greater than 1, then that's true. So if a is greater than b and a and b are greater than 1, then that's true. Okay, so this squared minus that squared is going to be positive, because this is going to be bigger than that. And so you got positive squared, which is positive, or positive, and positive divided by positive is positive, and therefore the answer is positive infinity, which again matches up with what we got on the other side. It's 36. So we have the limit as x approaches 4 from the negative side of x squared over x squared plus 16. So first thing you determine is whether there's a vertical asymptote, which there is not, because to factor this you'd have to have a solution of imaginary numbers. So there's no real solutions to this, therefore this never goes to 0, besides the fact that anytime you square any number, it becomes positive, and therefore positive plus positive is positive. So this always, and this also is always positive too. So at this point, you don't really have to do anything special. You just say there's no vertical asymptote, and therefore, if I just plug the number in and see what I get. So I do. So I just plug in p equals 4. Or x equals 4. I don't know where I got p from. X equals 4. And so the limit as x approaches 4 from the negative side is just equal to 4 squared divided by 4 squared plus 16, which is 1/2, because 16 divided by 32 is a half. Okay, where are we? 42. So 42 is the limit as x approaches 0 from the negative side of x squared minus 1 over x. So if you plug in x equals 0, you'll get 0 squared, which is 0, minus 1 over 0. So even though it looks like it may not be our typical function that has a vertical asymptote, it actually is. So one thing you could do is you could just break it up into two parts. You could say it's this limit of the difference is the difference of the limits. So you could say x goes to 0 minus that, and then you have minus the limit as x approaches 0 from the negative side of 1 over x. Okay, well, this one is not indeterminate, it's not undefined. You just plug 0 and you get 0. So the first is 0. So then all you have to do is do the second part. So if we look at this, if we come from the negative side of 0, then you're going to have a negative number. So 1 over a negative number is a negative number. So you're going to have 1 over a negative number. 1 is a positive number, so positive over negative is negative. And negative times a negative is a positive. And so the answer is positive, which means that this approaches positive infinity as x approaches 0 from the negative side. Let's go ahead and plot this thing just to prove that I'm not full of it. So we have, what's the equation? We've got x squared minus 1 over x. So there you go. So at x equals 0, it approaches positive infinity. And from x equals, approaching x equals 0 from the positive side goes to negative infinity. And what was the answer that I gave you? I said it was positive, so that's correct. So that's what that actual function actually looks like, which is kind of weird. How would you know it looks like that? Well, let's just go back. So we've got another way of doing it is you could find a common denominator. So what you would have is if you took this function, that, and then find a common denominator, which would be x, you'd have x cubed over x minus 1 over x. So adding the numerators, now you get x cubed minus 1 over x. So you can see that the function is undefined at x equals 0 because this goes off. But you've got a cubic equation in the numerator. And I think if you factor that, you'd have x minus 1 times x squared plus x plus 1. I think that's what it is. Let's just do that. Synthetic division. So let's start off with x cubed plus 0x squared plus 0x plus 1 or minus 1. And I'm saying a factoring on a negative x equals positive 1, or quantity x minus 1 is the factor. So I'm going to put 1 here. And so if we do the long division, or synthetic division, we bring the 1 down. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. Negative 1 plus positive 1 is 0. And so I end up with x squared plus x plus 1, which is this part right there. So that does work out, right? So it's got a x-intercept, x equals 1. You set x equal to 0. We have that vertical asymptote, so there's no y-intercepts because that's undefined at that point. Anyway, the reason it looks weird is you've really got x cubed minus 1 over x, and so it's kind of a combination of kind of like a cubic with a vertical asymptote shoved in there. Okay, we're 59. So that's a word problem. A patrol car is parked 50 feet from a long warehouse. The revolving light on the top of the car turns at a rate of 1/2 revolution per second. The rate at which the light beam moves along the wall is this. So R, it has units of feet per second, so it's like a velocity. 50 pi secant squared theta, the units are feet per second. It says find the rate when theta equals pi over 6. So basically you could say, so R of pi over 6, you just have to plug it in there. So you get 50 pi Okay, so anyway, sorry, stop there, just got a phone call. So anyway, we have the secant squared of pi over 6. And if you remember, which you probably don't remember, but if you remember the secant of theta is the same as the 1 over the cosine of theta. And so when cosine of theta goes to 0, then you have vertical asymptote. So we have vertical asymptotes at pi over 2 and 3 pi over 2 and continue on, multiples of, or addition of adding pi to each one of those things. And you could go negative 2, so it would be negative pi over 2. So those are where the cosine of theta goes to 0, therefore the secant of theta is undefined. So the first two questions are asking at pi over 6 and pi over 3, so you don't really have to figure where my cursor is. I can't see it. Oh, there it is. Okay, finally found it. So all I have to do is find the secant at pi over 6. Of course, that's not something you memorize, but the secant at pi over 6 is equal to 1 over the cosine of pi over 6. And that you may remember. How do we remember it? We draw the unit circle. We say that the sine of theta is equal to the y-coordinate on the unit circle, and that the cosine of theta is equal to the x-coordinate. So cosine is x. And then if you draw pi over 6 here, like that, that's pi over 6. It's pi over 3. It's pi over 6. Pi over 3. And then you look down here, okay, you say pi over 6, come down, it's that one that's closer to 1 than it is to the other way. Remember the numbers are 0, 1/2, square root of 2 over 2, square root of 3 over 2, 1. So those are the values for the sine at 0, pi over 6, pi over 4, pi over 3, pi over 2. So that's for the sine, and you can do it the other way for the cosine. So anyway, when you draw this line over here, pi over 6, you have to at least remember where that goes. You say, okay, this is not a half, it's not on this side, so it must be the other one. So the answer is cosine of pi over 6 is the square root of 3 over 2, which is the same as 2 divided by the square root of 3. And if you multiply by the square root of 3 in both the numerator and the denominator, you get that. Okay, so that's what the secant of pi over 6 is. So now you just plug it in. So R of pi over 6 is 50 pi times 2 square root of 3 over 3, which would be 100 square root of 3 over 3 pi. 50 times 2 is 100, and you have square root of 3 over 3. Okay. So that would be r pi over 6, and you can do the same thing at r pi over 3. So then you'd say, okay, you need to know what the secant of pi over 3 is. That's the same as 1 over the cosine of pi over 3, cosine of pi over 3. Let's go to unit circle. So here's pi over 3. Well, it looks like x equals a half, so it's a half. So you divide by half. Same thing as multiplying by 2, so you get 2. So the secant of pi over 3 is 2. So you get 50 pi times 2, which is 100 pi. And you know, this thing should be getting bigger as you go along. The light moves faster. So if you think about it, here I've got 100 times the square root of 3 over 3. Here I've got 100. So this square root of 3 over 3 has to be less than 1. And if you plug that in your calculator, you'll see that it is. So the square root of 3 divided by 3 is 0.577. So this is 0.577 times 100 times pi. This is 1 times 100 times pi. And then the final one, you have to do it as a limit. That's why this problem. So because so this approaches, so the question is, what is the limit of r as theta approaches pi over 2 from the negative side? And what you'll find out is that the secant of theta approaches infinity. So the secant squared of it approaches infinity, so the answer is positive infinity. I guess we forgot the units in here, feet per second. So basically what it means is as this thing's traveling, and if the light could go an infinite distance on the wall, and then the wall was an infinite distance long, then as you approach 90 degrees, this rate approaches infinity. So it starts moving slowly, and then it moves really quickly as you go further along the wall. That's the gist of it. Okay, the last problem in this section is this one that involves relativity. So basically what relativity says is that as the speed of an object approaches the speed of light, its mass approaches infinity. And so you end up having to expend an infinite amount of energy to do that. So that's why nothing that has mass can go as fast as the speed of light. The only thing that can go as fast as the speed of light is light, which has no mass. It's a wave, and it's also a particle. But anyway, light has no mass, but it does have energy. And anyway, that's another thing. But then the calculus problem is, you know, it says what is the, so the question is the limit as V approaches C from the negative side. It can't approach it from the positive side. And so what you would see is that as V approaches C, then this number approaches 1, 1 minus 1, or something, 1 minus something approaching 1 is going to be positive, but it's going to be a very small positive number as this occurs. So 1 minus, this is 1 minus something that approaches 1. So this becomes a very small number, and you take the square root, and it's still a very small number, and therefore you're dividing by a very small number, and therefore an m0 is the mass when it's at rest, so the mass approaches infinity. So that's basically what it says. So the limit of the mass as the velocity approaches the speed of light from below the speed of light equals infinity.